Hi all, welcome to KASHE channel. So in this video, I will explain about the sentence transformers and its applications. I am going to cover what are sentence transformers, what are their use cases, and some of the implementations for those use cases. Basically, sentence transformers are deep learning models. These models generate fixed length vectors for the given text or image. Those fixed length vectors are called embeddings. These embeddings are useful for a wide range of natural language processing and generative AI applications. I already mentioned these sentence transformers can take text or images. Here the embeddings generated from the sentences are the vector representations that capture the semantic meaning of those sentences. Similarly, embeddings generated from the images are vector representations that capture the visual features of the image. So in this case, the sentence transformer for both text input and image input generates a four-dimensional embedding. That means a vector which contains four values. Consider the sentences here. The cat sat on a mat. The cat was sitting on the mat. The dog was playing on the mat. If I supply these sentences to a sentence transformer, the sentence transformer generates corresponding embeddings. If I measure the similarity between the embedding 1 and embedding 2 generated from the first two sentences respectively, the similarity is 0.9967. In the same way, if I measure the similarity between the embeddings generated by sentence 2 and sentence 3, the similarity is 0.3835. So we got the more similarity between the embedding 1 and embedding 2 because the first two sentences are conveying almost the same meaning. The similarity between the embedding 2 and embedding 3 is somewhat less because the meaning between the sentence 2 and sentence 3 is somewhat different. In the diagram, each branch demonstrates how embeddings enable diverse tasks, including retrieval, clustering, similarity analysis, inference, and search across various data types. A wide selection of over 10,000 pre-trained sentence transformer models are available for immediate use on the Hugging Face platform. To get the embeddings, each sentence is passed through a transformer model. That model generates embeddings for each token available in that sentence, and then embeddings of all the tokens are passed to a pooling layer. Then the pooling layer generates a single embedding for the entire sentence based on the token embeddings. One of the examples for the pooling layer is average pooling. So in this example, I have supplied a sentence, I am a student, and the transformer is generating the embedding for each token. Every word is considered as a token here. Then the transformer model will generate four embeddings, one for each token, and these four embeddings are considered by the average pooling layer to generate a single embedding. This layer considers the average of four embedding values to get the final embedding. See various steps to use sentence transformers for getting embeddings. Step 1 is to import the sentence transformer class from the sentence transformers Python library. After importing the class, we need to load a pre-trained model using sentence transformer class. After loading the model, we can use the encode method to get a fixed length NumPy array, which is our embedding for the given input. This statement installs the required sentence transformers library, and this code snippet sets the environment variable Hugging Face API key from the collab secrets to authenticate Hugging Face models. Here I kept my API key as a secret in my collab environment. Now we will see how to load the model. First line of the code, import the sentence transformer class from the sentence transformers Python library. The sentence transformer class loads a specific pre-trained model named BERT base NLI means tokens. This model is based on the BERT, fine-tuned for natural language inference tasks and adapted for sentence embeddings. In the model name, the mean tokens indicate it uses average pooling to generate the sentence vector from all its token vectors. After loading, here we got the model object into a variable called model1, which is composed of two key components, the transformer, the pooling. The transformer has a maximum sequence length 128 tokens and the transformer model here is the Beck model. Here the pooling layer produces 768 dimensional embedding. That means here the embedding is a vector of 768 values. First we will see the generation of the embedding for a single sentence. Here the code snippet takes a single sentence, generates a numerical embedding vector that represents its semantic meaning, and then prints both the vector itself and its shape. It uses the pre-trained sentence transformer model loaded earlier in our code as a model 1 to generate an embedding for the sentence I love YouTube. Here the encode method takes the sentence as input and returns a numerical vector representation which is stored in the embeddings 1 variable. And the output shows the embeddings 1, the numpy array, and also it shows the shape. Here the shape is 768, indicates the embedding that is generated is of 768 dimensional vector. Note that the specific dimensionality depends on the pre-trained model that we are using. Now we will see how to generate the embeddings for multiple sentences. This code snippet takes multiple sentences, uses a pre-trained model to generate the embeddings for these sentences that capture their meaning, and then displays the dimensions of these embeddings. Here the first line creates a list named sentences and stores two sentences in it. I love YouTube, I hate YouTube. It uses the pre-trained sentence transformer model, model 1, to generate the embeddings for each sentence in the sentences list. The next line prints the shape of the embeddings to array. The shape tells us the dimensions of the array, essentially how many sentences were encoded and the dimensionality of the embedding vectors. There are two sentences and each sentence is represented by a 768 dimensional embedding. Next, embedding for an image. The code first imports necessary libraries for image handling and display. It loads an image using its URL from the internet. To perform image search, we need to load a multimodal model which supports both text and images. Here the sentence transformer class loads a pre-trained clip model from the sentence transformer library. Clip is a multimodal model capable of understanding both images and text. Finally, it generates an embedding for the loaded image using the clip model's encode method. This embedding is a numerical vector representation of the image features. The code then prints the shape of this embedding, indicating its dimensionality. Here the shape is 1, 512. It means that the clip model has represented the image as a 512 dimensional vector. So far we have seen generation of the embeddings from the text as well as image. Now we will see how to measure the semantic similarity. Sentence transformers can be used to compute the similarity between the sentences, images, and also between images and sentences. First we will see the similarity between the sentences. This code snippet generates the embeddings for the three sentences. I love mango, I love orange, I watch YouTube every day. The similarity method of the model object uses cosine similarity to compare the embeddings. Here the output indicates that the cosine similarity between I love mango and I love orange sentences is 0.7257 and the cosine similarity between I love mango and I watch YouTube everyday sentences is 0.2239. Here the value shows that the sentence 1 and sentence 2 are having more similarity and the sentence 1 and sentence 3 are having less similarity. Next, this code snippet compares the semantic similarity between the image and two sentences. The clip model is crucial here because we need to deal with both text and images. Here the output shows how semantically related the image is to each of the two sentences. That means the image is more similar to the first sentence and less similar to the second sentence. Note that we can also use cosine similarity function available with util module to find out the similarity between the vectors. Next use case we will see is semantic search. Semantic search seeks to improve the search accuracy by understanding the content of the search query. This is done leveraging the similarities between the embeddings. In the semantic search, similarity between that query embedding and all the embeddings of the corpus are calculated. Based on those similarities, we can get most relevant documents to our query from the corpus. This part defines the list called corpus. The corpus contains all our sentences. Here we use a pre-trained sentence transformer model, our model 1, to generate the embeddings for each sentence in the corpus. We define our search query as what is sentiment analysis. We then generate an embedding for the query using the same sentence transformer model, and the code uses the semantic search function from the sentence transformer's util module to find the most semantically similar sentences from the corpus to our query. Then the result variable contain a list of most similar sentences along with their similarity scores. In the final print statement, result of 00 corpus ID retrieves the index of the most similar sentence in the original corpus list. We got the corpus ID 6 as a most relevant sentence with a score of 0.7398 for our query. So by using this corpus ID, if we can retrieve the sentence available from the original corpus, the most relevant sentence for our query is sentiment analysis determines the emotional tone or opinion expressed in a piece of text. And the final application is document clustering. So in order to cluster the documents, first we need to use the sentence transformer to generate the embeddings for all the sentences available with the corpus, and then we can supply these embeddings to a clustering model to group similar documents as clusters. So in the code snippet, the list of sentences are stored in a variable called sentences, and this line uses our pre-trained sentence transformer model and converts all the sentences from the sentences list into the embeddings. And the code sets the desired number of clusters into 3, and these lines of code trains the k-means clustering model using the sentence embeddings. This model learns to group similar sentences together based on their embeddings. After the training, labels underscore attribute gives us an array where each element corresponding to the cluster assigned to each sentence. And this loop iterates through our original sentences and their assigned cluster IDs and prints them out, showing which sentence belongs to which cluster. And finally, this code snippet aims to separate the sentences into their respective clusters based on the cluster assignments. This allows us to see which sentences are grouped together.